Okay, so now continuing from where we left off in our last class, we looked at the third step, that was the magnitude slope contribution. So now taking over from the same question that we did, we see that we have the first part, that was the normalization that we did. Okay, this was the question that was given to us. Now the second part was the description that we did here. This was the second part, and the third part is the one that we just completed now, which was the magnitude slope plot. So this here is the magnitude slope plot, right? Now we know that when we talked about a Bode plot, we've got the magnitude as well as the phase plot, right? So this is what we're going to look at next. How do we create the phase plot? Okay. So now coming back, we just need to do a bit of a prep work for the phase plot. So you'll see that the phase plot contribution, this is how the slopes work. Remember, for the magnitude slope plot, it was minus 20 and plus 20 for the poles and zeros respectively. When it comes here, it becomes minus 45 and plus 45 degrees for the phase slope contribution. And with the increase in order, you just multiply it by 2. So if it's second order, it becomes minus 90 plus 90. If it's going to be third order, it's going to be minus 135 and plus 135. But like I mentioned, the scope of this study limits us to looking at just the first and second order, right? Next thing is, how are we going to draw the table? So here we have it. Now there's a slight difference here from the magnitude plot. In the magnitude plot, we saw that we had only one break frequency for each term. That was the break frequency, and then if a term started breaking at one point, it would continue breaking the whole way. Now, when it is a frequency or a phase plot, each term has got a start point as well as an end point. Now, how do you measure the start point and the end point? So the start point break frequency is equal to 0,1 multiplied by the break frequency of the term, right? And the end point is 10 times the break frequency. A pole or a zero term lying at the origin, it does not have a frequency, a break frequency. So that means the pole or zero lying at the origin is not considered when we look at the phase plot. All right. So what we're now going to do is we're going to go back to our problem, and we're going to list the terms that are going to play a role in the phase plot, right? So we already mentioned that the pole at 0, it's no longer going to play a part. So it's going to be, again, in the descending order, it will be pole at minus 1, pole at minus 2, and 0 at minus 3. So this is what we're going to be working with in the next section, right? So let's just bring that table that we have here to determine the start point and the end point. So let's just take these two terms. Let's in fact take the whole stuff, and let's bring it here so that we can use it as reference when we are doing our work. Okay. Right, so there we have it. So each term has a start point and the end point. So let's first of all just create the start point and the end point. So the pole at minus 1, let's call this as the start point, the end point. And let's just draw a line to separate these two. Then you have the pole at minus 2, and then you have the 0 at minus 3. Okay, so let's see. So the start point, they say, is, okay, let's first of all write down the break frequencies here. This is 1 radians per second. this is equal to 2 radians per second, and the break frequency here is 3 radians per second. Now the pole at -1, what is the start point? So the start point is 0,1 multiplied by the break frequency. I'm talking about the pole at -1, right? So that means it is 0,1 multiplied by 1 radians per second, which is equal to 0.1 radians per second. And what is the end point? The end point is equal to 0.1 comma, sorry, it will be, if you have a look, 10 multiplied by the break frequency. So in this case it will be 10 times 1 radians per second, which is equal to 10 radians per second. Okay. Likewise, if we do for all of them, you'll see that this is now going to be 0.1. I'm going to just say radians per second on top, so that we all know that the units are 0.1 radians per second, then 10 radians per second. In this case it will be 0.2 radians per second and 20, and over here it will be 0,3 and 30. Now based on this info, we are now going to create the slope table, right? Oops. Right? So we're going to be creating the slope table. So let's do this, sorry. Now we need a slightly longer table here because we've got more terms coming in, right? So you have your description, that's going to be here, description, and then you have your first term, which is your pole at -1, your pole at -2, 0 at -3, and then finally you have your total. So here you have pole at -1, pole at -2, 0 at -3, and then you have your total here. Now we're going to start with in the order. I'm going to say radians per second here because units are very important. There are no units, then you'll get no marks here, so please be careful. And then I'm going to put down the lines. Oops, sorry. 0.1 radians per second, 0.2 radians per second, 0.3 radians per second, 10 radians per second, 20 radians per second, and 30 radians per second. So let's fill that in. So this will be 0.1, 0.2 in that order, 0.3, 10, 20, and 30. To make it a bit more understandable, let's do it like this. Let's put it in different colors here. This is 0.2, and this here is 0.3. Right? Now, this is the start point for the red one, is the start point for pole at -1. So the end point, let's put it in red as well, it's at 10 radians per second. The start point for the pole at -2 is at 0.2 radians per second, and the end point is at 20 radians per second. And the start point for the 0 at -3 is at 0.3 radians per second, and the end point is at 30 radians per second. Okay, so that's sorted out. So let's bring that to the side here as we continue our work. Alright, now let's bring in the table that we had created here. Yeah, this is the table for the phase slope contribution that we have. Oops, let's bring that here. Yeah. Okay. Now, the start point for the pole at -1, it is a first order term. So let's indicate in red. It will be -45, -45, -45, and when it reaches 10, it is then ending. At 10 radians per second, it's ending. So there's nothing there, right? Now for the pole at -2, nothing happens to it at point 1 because remember the start point is at point 2, right? At point 2, because it's a first order term, it's going to be -45. It's going to continue at point 3. It's going to continue at 10. But when it reaches 20, that's when that one is done. Because that's the end point, right? Now, the 0 at -3. At 0.1 radians per second, there's nothing. At 0.2 radians per second, there's nothing. At 0.3 radians per second, there's -45, -45. At 20 radians per second, it's again -45, but at 30 radians per second, it's ending, right? And then we have the total, which is going to be -45. Let's put it in a different color here. Let's put it in purple. -45, -90, -135, -90, -45, and then 0. So ladies and gentlemen, this is your phase slope plot that we have here, right? One way to keep yourself right, you'll always see that this triangle that is formed here, right? And this triangle that is formed here, this one here. Okay, that's not exactly a triangle, but you get my point. The pattern needs to be the same on both sides. If you get a mixed pattern like a 45 here, then there is a slight problem with the work that you are doing. But this is how you do the phase slope plot that we have. Right, so let's now continue and complete this for the self-assessment for the question that I did ask in the previous lesson. Yeah, so you should have been done with the magnitude slope plot for that question. So now we continue. The question was k into s plus 4 divided by s into s plus 2 into s square plus 5s plus 25. So now let's continue and do the phase slope plot for this one. So that should conclude how we do the asymptotic approximation method. And once you're done, we'll do one full problem as well. Alright. Okay.